Let's move offshore just a little bit and talk about ocean basins and sediment deposition into those ocean basins. These are the lowest points on Earth's surface, ocean basins are, so they are easily the areas where you can get a lot of sediment collection. Here's a diagram of some of the parts of an ocean basin. So the coastal plain is not a part of an ocean basin, but it is the low part of, say, a passive coastline that slopes toward the beach itself. Then just offshore, you have what is called the continental shelf, the area of relatively shallow water that extends for a ways until you hit what is called the continental slope and the continental rise, which is sort of the piles of sediment at the very edge of that continental shelf. And then the abyssal plain is the relatively flat, not completely, but very deep part of the ocean. And this is usually several kilometers deep, maybe 4+ kilometers. The continental margin refers to the shelf, slope, and rise, and the abyssal plain then is separate. The width of the continental shelf is wider for those passive coasts, coasts without tectonic activity. We can think about the type of crust that's underlying all of these. We talked about how continents tend to be underlain by continental crust and oceans by oceanic crust, but it's a little more complicated than that, because it turns out that continental crust underlies most of the continental shelf, and then to varying degrees in various points on Earth's surface, this boundary may shift. The boundary between continental crust and oceanic crust tends to be somewhere in between the slope and the rise. But once you get on to the abyssal plain, you're definitely on oceanic crust. The usual depth of the continental shelf here is going to be somewhere under 130 meters depth. So it's about 400 feet. So really the water offshore along passive coastlines tends to be pretty shallow still for many miles, 75 kilometers just about on some of these passive shorelines, but it can be, you know, as much as 2 or 3 times that in some spots. You may also see these things called submarine canyons that cut across the shelf, the slope, and the rise, places where for one reason or another, water and sediment has cascaded down that canyon in the past. It's a little bit like an underwater river. Kind of cool. You can see some of these if you go looking in Google Earth. You'll see some of these submarine canyons. A particular type of deposit that is interesting in geology are these things called turbidites. These are the deposits that form along those submarine canyons from submarine landslides that transport that continental shelf sediment, it's got some sand and some mud, onto the continental slope and rise. And these things can have a very complicated morphology, but really what I want you to get is that you have erosion in the quote unquote headlands on the continental shelf, and you have deposition occurring further down on the slope or the rise. And it can extend all the way out to the edge of the abyssal plain. Turbidite deposits you can actually find on land pretty often from periods in time when sea level was a little bit higher generally, or because they've been pushed up on shore by tectonic activity. But they have a very common, very similar profile to them that's worth discussing. So, excuse me, at the very base of a turbidite deposit, you'll usually see an erosional surface, right? Some sort of an unconformity, which indicates that water was rushing past, eroding that pretty strongly at the start of this turbidite, this submarine landslide. And then slowly over some minutes to hours, that water slows down. And what happens when the water slows down? It dumps its largest sediments. So just above that erosional layer, you'll see sand to maybe some gravel at the very base. And then particle size decreases as you go up the turbidite deposit because more sediment is being deposited, the water is being slowed down more and more until you get into these sort of wavy silt layers. So you've got much finer particles. And then on top of that, the water basically slows down and stops and settles, and all the sediment that was remaining in that turbidite flow very slowly settles out, and you get mud deposited on top of that until you get another turbidite forming on top. And so here's what one of those looks like, right? You see the unconformity down here, you see the sand then above that, and then you see finer and finer particles going into these wavy silt deposits above that. So this would be sort of a fossilized underwater landslide, and that's what a turbidite is. I'd like to point out a couple features of the abyssal plain as well, because despite being called a plain, it is not perfectly flat. It has a lot of interesting features on it that we really only started to discover once we had sonar and radar, things like that, that we were developing during World War II. And then we could turn those on the seafloor and discover all the complications of what the seafloor looks like. So it's got these mid-ocean ridges, right? And if those are at a mid-ocean ridge, these are places where the divergent boundary is. And it's generating new crust there, and that crust is hot. And so it tends to stick up a little bit because you're piling more crust there and it's warm, so it's expanded a little bit. And then in the center of that, you'll have a mid-ocean rift valley. But for the most part, the elevation around that mid-ocean rift is a little bit higher than at other points on the abyssal plain. And they run in a line separating two plates that are divergent boundary. You'll also see some isolated volcanoes, or sometimes you'll see lines of them, volcanic arcs that are formed on oceanic convergent boundaries. And some of those volcanoes rise above the water, and some of them are sort of stay below the water, but they can still erupt. And you'll also find trenches, places near maybe some of those volcanic arcs or near where ocean continent convergent happens. And those trenches are places that one of the oceanic places is diving deep below the other plate, and that creates the deepest parts of the ocean actually occur at those convergent boundaries along those trenches, those places where the one plate is subducting under the other one. Here you see a slightly better image of what one of those convergent plate boundaries might look like. And if I extend it a little bit here, you'll see exactly where that trench sits at the boundary of those. And then behind it, you get the volcanic arc forming. So that line of volcanic islands that forms where this oceanic crust and this oceanic crust is converging. Some notes about some general ideas of sediment deposition offshore. So we have, remember what clastic sediment is? Those are pieces, wholesale pieces broken off of other things like clay or sand or silt or gravel. Those are clastic sediments. Generally, the further offshore you move, the finer those particles get. So your sands will be nearer to shore, and then you will grade into silt and then shale, right, clay dominant stuff as you get further offshore. And then eventually, if you run out of those clastics, they all get deposited. You might deposit some limestone in the deepest waters. So a lot of times, if we go and we are reading the rock record, we can tell what was happening to sea level at that spot by interpreting the size of the particles. Near shore, the particles can be moved by the waves because it's deep enough that the sands are above the wave base, and so they can be moved around by those waves. And then as you go further and further offshore, you're going to get into the mud and then eventually into the limestone. But if you look at a sequence of rock and you see that at the bottom, the oldest ones are sand, and then you have silt and then limestone, that's indicating that when the sand forms, you're near shore, silt forms, you're a little further offshore, and then when the limestone forms, you're the furthest offshore. And so this would be a case where sea level must be rising because you're getting further and further offshore. The sea is rising further and further above these sediments that they're being deposited. And we call that, what did we call that before? A transgression. The opposite of that would be a regression, or we could call it prograding, because sediment is coming off of shore and relative sea level is falling, often because the sediment is just burying that coastline a little bit. So in these situations, you start with limestone, you're deep, and then you go to shale, you're a little shallower, and then you go to sandstone, where it's the shallowest underwater still. And so you can recognize this is just a very sort of general introduction to reading some of those sedimentary facies, is looking at, is sea level rising or falling over time in the spot, simply by looking at the sizes of the sediment particles. Of course, if you really go into this and you look at it in detail, it turns out there are a lot of these different environments that you can get all these clastics and the limestone carbonates deposited in. So it's not quite that simple, but that is often a point where we start by saying sand is deposited on the shore face, then shale, silts, clays are deposited below wave base, but near shore, still on the continental shelf mostly. And then the limestones are even further out on the continental shelf, or even into much deeper water than that. Okay, folks, thanks for sticking around and listening to me talk about coastlines and ocean basins and all the things that are affecting them. I will see you online.